Good morning. Today we're going to be looking at quadratic sequences. So these are sequences which have nth terms of powers up to n squared. So for example, the sequence n squared plus 3n plus 9, that would be an example of a quadratic sequence. So my first question for you today is, I want you to think about what would the first quadratic sequence you ever learned have been. So you can pause the video if you need to. So what's the first quadratic sequence you ever learned? You probably learned it in year 7. So, I'm willing to bet the first quadratic sequence you ever learned was this: 1, 4, 9, 16, 25. Okay, do we recognise those numbers? We should do, because these are our square numbers. This is the sequence n squared. So 1n squared, it's just the square numbers. Right? So, think about this sequence below the sequence n squared. If 1n squared is 1, 4, 9, 16, 25, how do these numbers compare to that 1n squared sequence? So how does 1 compare to 2, 4 compare to 8, 9 compare to 18? What's going on here? Do we notice a link between these sequences? Okay, so the link we should have noticed is this. Each term in the second sequence is double my first sequence. So if 1n squared is 1, 4, 9, 16 and so on, 2n squared is just double that. It's 2, 8, 18, 32, 50 and so on. Okay, so quadratic sequences, they work very similarly to linear sequences. If you double the nth term, all the terms in my sequence just double. Okay, so make a prediction here. If 2n squared is this, what would the sequence 2n squared plus 1 look like? Okay, so I'll give you a few seconds to think about it. And at any point, just pause the video if you need to. So the sequence 2n squared plus 1 would look like this. It would be 3, 9, 19, 33, 51, and so on. You notice just every term in that previous sequence has just had 1 added onto it. So a common type of question is something like generate the first 5 terms of a sequence. I think the easiest way to do this is to replace n with the term number you're looking for. So we make a substitution. So, for example, if I want to find the first term, instead of n squared plus 2, I'm going to call it 1 squared plus 2, because I'm looking for the first term. So 1 squared plus 2 would give me 3. The first term of this sequence is 3. To find the second term, instead of n squared plus 2, I'm going to call it 2 squared plus 2, because I'm replacing n with the term number I'm trying to find. So my second term would be 6. So to find the third term, I would do 3 squared plus 2 to get 11. The fourth term would be 4 squared plus 2 to get 18. And the fifth term would be 5 squared plus 2 to get 27. Right? So, if you need to pause the video, please do that. And I want you to generate the first 5 terms of the sequence n squared minus 2. Okay, so your first 5 terms should have been negative 1, 2, 7, 14, and 23. Okay. And it's interesting actually, because we know the sequence n squared would be 1, 4, 9, 16 and 25, and when you think about it, the sequence n squared minus 2, which you've just found, it does fit that rule. It's just 2 less than our square numbers, so that's a shortcut that we could have used as well. Okay, so for our first task today, what you're going to do, could you spend about 10 minutes on this task, please? Do as much as you can. And I want you to generate the first 5 terms of each of these sequences, please. Alright, so moving on, I'm going to show you how to find the nth term of a quadratic sequence. So I'm going to do 4 worked examples. It's completely up to you how you do this. You can just watch me do all 4 if you like, or if you feel like you're getting the hang of it after question 1 or 2, you're welcome to pause the video and try it for yourself. But these are the 4 examples I'm going to give you, and then afterwards you're going to move on to task 2. Alright? Okay, so for question 1, just like what we do with linear sequences, what we're going to do, we're going to ask ourselves, well, what does the sequence go up in every time? Alright, so to get from 3 to 12, we've added 9. To get from 12 to 27, we've added 15. To get from 27 to 48, 48 take away 27 is 21. And then to get from 48 to 75, we've added 27. Alright. this is where it gets a bit interesting, because we're used to sequences going up by the same amount each time. So from last lesson, that's what a linear sequence would be. But with quadratic sequences, they've got quite an interesting property. What we're going to do, we're going to look at the second difference. To get from 9 to 15, we add 6. To get from 15 to 21, we add 6. And to get from 21 to 27, we add 6. Okay. Any quadratic sequence has a second difference that is always consistent. Right, so that's an interesting property. So the second difference is plus 6 each time. What we do at this stage, if we want to find the nth term of a quadratic sequence, what we need to do, we halve the second difference and compare. So I'm going to write this down. So our sequence is 3, 12, 27, 48, and 75. And we're going to compare it with the sequence 3n squared. The 3 happens because I halve the second difference. The second difference is 6. I'm going to halve it. So I'm going to compare my sequence with the sequence 3n squared. And let's see how far off we are. Okay, so 3n squared, well, 3 lots of 1 squared gives me 3. 3 lots of 2 squared, so to find the second term, 3 lots of 2 squared gives me 12. 3 lots of 3 squared gives me 27. 3 lots of 4 squared gives me 48. And 3 lots of 5 squared gives me 75. And actually, I can see that our sequence and the sequence 3n squared are identical. So my answer is 3n squared. This sequence here is the sequence 3n squared, because I've halved the second difference and I've seen that there's no difference at all between our sequence and the sequence 3n squared. Alright, so for question 2, I've seen what it's going up by each time, and that's not consistent. So I'm starting to think this might be a quadratic sequence. For me to test that, I'm going to find the second difference. So to get from 9 to 15, I've added 6 each time. To get from 15 to 21, I've added 6. And then to get from 21 to 27, I've also added 6. Alright, so it's looking a bit better now. I can see that I've got that consistent second difference. So that tells me that this is a quadratic sequence. So thinking back to question 1, I know at this point I halve the second difference and compare. So I'm going to write out my sequence to start off with. So our sequence is 4, 13, 28, 49, 76. And we need to halve the second difference. So we're halving that 6 to get 3, so we're interested in 3n squared. This tells me that my sequence, it's something to do with the sequence 3n squared. Let's see how close we are. So the sequence 3n squared, well, 3 lots of 1 squared gives me 3. 3 lots of 2 squared gives me 12. 3 lots of 3 squared gives me 27. 3 lots of 4 squared gives me 48. 3 lots of 5 squared gives me 75. So I'm asking myself, how does our sequence compare to the sequence 3n squared? Okay, so our sequence starts with a 4, but 3n squared starts with a 3. The second term in our sequence is 13. The second term in 3n squared is 12. We're noticing that link. And there's a very easy, quick way to find that link. We're going to make a subtraction. Let's take away 3n squared from our sequence. 4 take away 3 gives me 1. 13 take away 12 gives me 1. 28 take away 27 gives me 1. 49 take away 48 gives me 1, and so on. I can see that our sequence is just 1 greater than the sequence 3n squared, which means that our sequence must be 3n squared plus 1. So this sequence is 3n squared plus 1. That is my nth term. Alright, so for question 3, so I've started us off, so I've figured out, well, what's happening each time. It's not consistent, so this might be a quadratic sequence. Let's check and see if the second difference is the same. To get from 9 to 15, I add 6. To get from 15 to 21, I also add 6. To get from 21 to 27, I also add 6, which tells me this is a quadratic sequence. So thinking about the last two questions, I know at this stage what I need to do to find my nth term. I halve the second difference and compare it with our sequence. I've written out our sequence, so this is just the question, I've written it out, and I need to halve this second difference. If the second difference is 6, I'm interested in comparing our sequence to 3n squared, because half of 6 is 3, so that's what halve the second difference means. Okay, so how does our sequence compare with the sequence 3n squared? So just using my previous working out, so I know that the sequence 3n squared is 3, 12, 27, 48, 75. I can work that out by substituting. And now what I'm going to do, I'm going to ask myself, well, how does our sequence compare to that sequence 3n squared? If I use that subtraction method that I used in question 2, well, 9 take away 3 gives me 6. 8 take away 12 gives me 6. 33 take away 27 gives me 6, and so on. So what this actually means is that our sequence, it's always just 6 greater than the sequence 3n squared. No matter what term I'm comparing with, we can see that our sequence is always just 6 more. So our sequence is exactly the same as 3n squared, but it's just had 6 added to every term. That's what I've worked out. So I can say my sequence, my original question, it's 3n squared plus 6, because it's the sequence 3n squared with 6 added on to every term. So this is my answer. So it's 3n squared plus 6. All right, for the last question, so question 4. Again, it's not going up by the same amount each time, so this is probably going to be a quadratic sequence. So let's just check to get from 9 to 15. Yeah, it's just going up in 6s, just like the last few questions. I've got that consistent second difference. So what I do now, I halve the second difference and compare it with my sequence. So half of 6 is 3, so I'm going for 3n squared. And I know through the last few questions that the sequence 3n squared is 3, 12, 27, 48, 75. I can work that out through substitution. All right, so how does my sequence compare with the sequence 3n squared? If I use that subtraction method, so let's subtract and see what happens. Negative 3 take away another 3 gives me negative 6. 6 take away 12 gives me negative 6. 21 take away 27 also gives me negative 6, and so on. So I can see that my sequence, it's always 6 less than the sequence 3n squared. So no matter what term I'm looking at, so every term in the sequence 3n squared, so my sequence is just 6 less than that. So my nth term would be 3n squared minus 6. That's what my answer would be. So this is the sequence 3n squared minus 6. Okay, so here are your solutions all together. Just notice those interesting links between these answers. Right, so the first one was 3n squared, and the next one was 3n squared plus 1. Can you see how we could maybe have predicted that before I'd done all that working out? So 4 is 1 more than 3, 13 is 1 more than 12, 28 is 1 more than 27, and so on. So again, 3n squared plus 6. Do we notice that this sequence here is just 6 more than every term in my first sequence? And again, 3n squared minus 6. Every term in this sequence is just 6 less than each term in my initial sequence. Right, so those are the solutions, and that's just an example of how these questions are linked. And in task 2, all of these questions are going to follow a similar pattern, really. So you're going to find some interesting results in your answers. So what I want you to do as you work through task 2, use the method that I've shown you, and ask yourself, what is the relationship between these questions? Can you explain these patterns as they're occurring, please? All right, thank you very much. Let me know if you need any help.